Assalamualaikum, my name is Nur Anasatira binti Abdul Aziz. My matric number CUF21002X. So I will present about objectives. So for our objective is to efficient and cheaply design structure component. 2. To reveal the component part of a structure design. And 3. To gain knowledge of Eurocode complete building design process. So this is our design parameter. So you can see our design parameter that we use.
Assalamualaikum and hi, my name is Nur Aisha Fariha binti Kamar Zaman. My matric number is DF210027. I will show the layout plan drawing of our project. So this is our structural drawing for ground floor, and first floor to third floor plan is same, and last drawing is roof floor plan. Then this is our architecture drawing for all floor.
Hi and Assalamualaikum. My name is Nur Shamina Afika binti Sharizan. My number matric is DF210072. So for now, I will explain about our project, which is the part of Esteem 3D model. So the Esteem 3D model is generated by referring to the structural layout plan drawing, which is we have to refer the dimension of the building and also the other parameters such as column and also the location of the beam. By using the Esteem software, we also can analyze our structure member, and also we can analyze the wind load calculation, which is to support the frame analysis for the arm brace part. And then we by using the Esteem software, we also can support our manual calculation that we have given in the report of project. And then based on the figure given, this is the picture of the front, top, bottom, and also the isometric view of our building, which is consists of 4-story building. Next, this is the 3-dimensional illustration of our building in this project. So for this part, we have used the apps that call as Google SketchUp. So in the Google SketchUp, we can use to generate the 3D model view for our building. So the function or the purpose that we use the Google SketchUp is to see the clearer vision of our building, and also to demonstrate the purpose and the function of our building, which is as the function of office building and also as the parking lot.
Hi and Assalamualaikum. My name is Nur Shami binti Norsha and my matric number is DF2100011. So today I would like to present about our slab calculation for this project. So the first one is our slab first calculation in 3-4 at BC slab is about two-way restraint slab. So the first thing first, we need to divide our long span and short span to get our types of slab. So our calculation is got 1.0, which means two-way slab. So the next one is action. For the action, design action is 9.59 kilonewton meter per m cube. So our analysis section, our case is case 2, which is one short edge discontinuous. And for our bending moments, we have two span, which is short span and long span. In short span, we have two value, which is 8.11 kilonewton meter per m and 10.91 kilonewton meter per m. So at our long span, we have 7.83 kilonewton meter per m and 10.35 kilonewton meter per m. So this value actually at midspan and support value. So next we go to main reinforcement, which is for our effective depth. For dx is 94 mm, meanwhile for our dy is 82 mm. So next is our minimum and maximum reinforcement area. So our AS minima is 126 mm, meanwhile our AS maximum is 5000 mm cube per m. So our secondary bar provided is 185 mm cube per m, which is using H10 425. So our short span having two value, which is for our mid span is our AS required 209 mm cube per m, and our AS provided for this mid span is H8 200 for bottom. The value is 251 mm cube per m. So for our support, for AS required is 281 mm cube per m. Meanwhile, our use or our provided AS is H8 125 top at top and value 402 mm cube per m. Next is our main reinforcement for long span calculation. So we have mid span and our support. So there is two value required, which is our mid span is using 7.83 kilonewton meter per m, and our AS required is 231 mm cube per m. Meanwhile, for our AS provided using is H10 300 at bottom, which is in value 262 mm³ per m. Meanwhile, for our support using 10.35 kilonewton meter per m, and our AS required is 309 mm³ per m, and our AS provided is using H10 and 250 at top. In value is 314 mm³ per m. So for our shear force calculation, for our short span only have one value, which is 18.64 kilonewton per meter. So for our long span, using having two calculation, which is 18.64 kilonewton per meter, and our second value is 12.34 kilonewton per meter. So our design shear force, which is VED, is using 25.90 kilonewton, and our design shear resistance is 49.8 Newton. So our V minimum is 49.4 kilonewton. So our VRDC is acceptable because it's larger than VED. Next is about our deflection calculation. So for this, P calculation, percentage calculation is 0.002. Meanwhile, for our reference reinforcement ratio or P knots is 0.005. So for our factor for structural system, okay, is 1.3. So our LD calculation, we got 76.88, and our modification factor for 7 meter is 1.0, and modification for steel area provided, we got 1.20, which is less than 1.5, and our allowable span effective debt ratio is 92.26, and our actual span effective debt is 5744, which is less than our LD allowable. So this is acceptable. And next, our last calculation for slab 1 is cracking. For cracking, we use the our main bar and secondary bar is also acceptable, and at the picture also show our detailing for this calculation. So next is our slab 2 calculation, which is located at 1, 2, and at BC slab. So for this calculation also about two ways restraint slab also. So the first thing first, we need to divide our long span and short span, and our calculation got 1.98 for this slab, which is still in two-way slab, but in different case. So the action also is quite similar from the first one, which is 9.5 kilonewton per m. Okay, and our analysis for this calculation, our case is case 9, because for edges discontinuous. So for our bending moment, we only have one value for short span, which is 8.05 kilonewton meter per m, and also for long span also have one value, which is 4.06 kilonewton meter per m. So for our main reinforcement, which is our effective depth, also quite the same with the first one, which is dx, and our dx is 94 mm, and our dy also 82 mm. So our minimum and maximum reinforcement also is still the same, like the first slab, which is our AS minimum is 126 mm, and our AS maximum is 5000 mm cube per m. But our secondary bar is quite different, which is we're using H10 200, which is the value is 393 mm³ per m. And our calculation for main reinforcement in short span is only focused on mid span. Our AS required is 207 mm³ per m, and our AS provided is using H8 175 in value 287 mm³ per m. So our long span value for the mid span calculation is 4.06 kilonewton meter m, and our AS required is 120 mm³ per m, and our AS provided is using H8 300 in value 168 mm³ per m. So for our shear calculation, quite simple because we only have one value for each short span and long span, which is now for our short span is 13.90 kilonewton per m and our long span is 8.70 kilonewton per m, and our design shear force is 13.90 kilonewton, and our design shear resistance is 44.6 kilonewton, and our V minimum is 46.5 kilonewton. So our VRCD is more than VED and it is acceptable. So our deflection calculation for percentage of required tension reinforcement, our percentage is 0.002 and our reference reinforcement ratio is 0.005, which is our factor for structural system is K equal to 1.3, and our modification factor for 7M is also 1, and our modification for steel area provided is 1.39 and still below than 1.5. So therefore our allowable span effective depth ratio is 106.86, and our actual span effective depth is 29.25. So our actual span effective depth is quite less than our allowable LD allowable. So this is acceptable. So next is our cracking and detailing for this project. As we can see, it is okay and acceptable also.
I will present the column calculation for two types of cases in our project. This calculation is to make the column detail according to the criteria required to prevent the building from collapsing or swaying. So this is our first type, which is on the side column located at 3A. To get the column detailing, we must know the value of axial force and moment, the specification that we already provided as shown in the body diagram. The size and length of the beam, size column, GK and QK for each floor also given. So first, we calculate the maximum and minimum ultimate load at each floor to know the total column load at one location from ground floor to roof. And the total load is 702.6 kilonewton. Next, we find the bending moment for z-axis. The stiffness formula is BH power of 3 per 12 per L, and the column for height 3 meter is 2.25 multiplied with 10 power of 5. For 1.5 meter is 4.5 multiplied with 10 power of 5, and for beam 5.4 meter is 1.25 multiplied with 10 power of 5. The difference moment for FEM is 24.61 kilonewton meter, and W come from this calculation. After we get all the information for moment in z-axis, we can calculate their upper and lower column by using this formula. Then, we do the same step to get the moment in upper and lower column for y-axis, but the stiffness formula are different with z-axis, which is HB power of 3 per 12 per L, and the moment for y-axis just at one side. So this is our body diagram for column moment in this location. Next, we determine the classification of column, which is cylinder or non-cylinder column, to know the failure modes. The specification as shown in this slide, and the calculation considered at ground floor to first floor. From formula moment of inertia, we get column z-axis and y-axis is 6.75 multiplied with 10 power of 8 millimeter power of 4, while for main and secondary beam is 2.08 multiplied with 10 power of 9. The value of stiffness EI per L for column at both axes is same, which is 2.7 multiplied with 10 power of 5 millimeter power of 4, while at both beam also same, which is 3.8 85 multiplied with 10 power of 5. Next, the relative column stiffness for both axes is more than 0.1. So we use the larger value to calculate the effective length of column. Then, last calculation is slenderness limit. This is their formula, but for A and B already given in EC2. So after put all the value in that formula, we know that our column at both axes are non-slenderness because lambda limit more than slenderness ratio. So we design the moment for non-slenderness column and choose MED with the maximum value between M2 or M min due to moment Due to movement occurring on both axes, the biaxial bending should be checked. So for this part, we must check biaxial bending because the value that we got is more than 0.2, while for this formula, we ignore it because 1 is less than 2. This is to prevent problems from happening. However, reinforcement design should be calculated first by using this step for moment in both axes, and the AS that we provide is 452 mm square with bar 4H12 more than AS required, and 452 mm square is in the range of AS min and AS max. Bar spacing in column also known, which is HC with spacing 225 and HC 125. Then we check the biaxial bending, and after check it, we can confirm that the number and type of bar used is safe because the last value we got is less than 1. So this is the detailing for column 3A. Next, the second type is located at the middle, which is 3C. The calculation is similar with the side column, but there are also some differences, like at the column load for this column is 711.83 kN. This is because the length of the location is different like before, and their bending moment have separate into two parts in both axes, while for column 3A at y-axis just have only one part. Then, after calculate FEM, moment in upper and lower column, this is the body diagram with the value moment that we got at each axis. For moment Y, we got like this because the FEM at two part is same, and after we differentiate it, we got 0 moment. Next, we check the classification for this column, and this is the specification and body diagram that we use. For this step, also same like previous type, but the calculation for stiffness at secondary beam is different due to the length and two part of secondary beam. So the slenderness limit for Z and Y axis are different, but the output is same, which is their classification is non-slenderness at both axes. However, the design moment in this column only at Z-axis that we assume as major axis due to the square column, and we got MED is 16.69 kN. Since bending occurs in one direction only, biaxial bending does not need to be calculated. Then we continue on the reinforcement calculation, and we got the ASFYK per BHFCK from design chart is 0. So AS required also 0, but we still can see the AS min and AS max to provide the bar, which is 4H20 with the area of 1257 mm square, and the bar spacing is HC 300 and HC 175. Therefore, This is the detailing for our column at 3C.
So next I will present about frame analysis and I calculate 3A until E. So for action, total permanent load we get 4.325, and for span 1 is 26.06, span 2 is 23.85, and span 3 is 23.85, and span 4 is 26.06. So next we move to data. So you can see in the slide, so just calculate the stiff fry, so joint A until joint E. Okay, for cases 1 to 5, this calculation method is the same, but I will only give one example. So for cases 2 until 5, use the same method only. So the first one is we calculate the feed and moment, next moment distribution, next shear force, and the last one is shear force and bending moment diagram. For the last one, we just draw the shear force envelope and bending moment envelope and just enter all the value on this draw.
Hi, so for now I will explain about the calculation of frame analysis, which is the umbrace part. So firstly, we have to calculate the wind load, and the specification that we have used in this part is the average roof height is assumed as 12 meter. The width and length is based on the dimension of the building. The location is at the Mersing, which is zone 2. The terrain is flat area and the slope is less than 0.05. The construction is as mentioned in the instruction, which is reinforced concrete. The sway frequency is 0.2 Hz, mode shape 1.0, and the average building density is assumed as 160 kg per meter cube. So firstly, we have to obtain the value of P, which is design wind pressure, by obtain the value of design wind speed, aerodynamic, and also aerodynamic coefficient, and also the dynamic response factor. And then after we obtain all of the value, we will get the value of MZCAT, which is for our calculation. The MZCAT is 0.86. It is because our H is 12 and the category for our building is category 3 suburban area. And then after we obtain the value of MZCAT, we will obtain the P value for windward and leeward, and then we will get the value of the total. So as the figure given, each of the floor has its windward and leeward pressure. So for the first level, the total kilonewton per meter square for level GF is 1.392. So for level 1, 1.430. For level 2, 1.507. For the level roof or 3 is 1.610. Next, we move to the cantilever method, which is under the lateral load analysis. So the location that has been selected is C1 until 4. So firstly, we have to calculate the design wind load for each floor level of subframe on the location selected. So the formula is 1.2 WK. So each level will get the design wind load, and then we also has to obtain the value of center of gravity of the structure, which the total length of the building on the location selected will be divided into 2. So the center of gravity structure for our building is 6.78. Next, after we obtain the value of center of gravity, we have to determine the distance from centroid for each column 1 until 4. And then we will obtain the column axial load value. After we have obtained the value, we will proceed with the each level, which is we have to start from the level above, which is level 4 and above. So firstly, we have to calculate the axial force in column to determine the value of P. So for the level 4, P that has been obtained is 0.36 kilonewton. So when we get the value of P, we will enter the value of P into the column axial load that we have calculated before. So next, we also have to calculate the shear force in beams and column for the level 4. So the purpose we have to calculate the shear force in beams and column is to determine the value of F1, F2, F3, H1, H2, H3, and H4. So the step is to consider the subframe to the left F1, F2, F3, and then we have to calculate the summation of FH to get the H4. And then the next level will be proceed same as the calculation before. Next, we proceed the calculation with the one level subframe calculation, which is to calculate the vertical load only. So the selected location is C1 until 4. So the specification that we will use in this calculation is the loading, which is finishes 1.2, unit weight concrete 25, imposed load 2.5, and the dimension of slab thickness 125 mm. Beam size is according to the drawing, which is 200 times 500 mm, and the column size is 300 times 300 mm. So firstly, we have to calculate the action, which is loads on slab, which is N, and then we have to obtain the GK and QK. So then we have to determine the loading distribution for each slab by determine whether the slab is two-way or one-way, and then determine the case. After we have determined the case, we have to find its shear coefficient for each slab by referring to the EC books, and then we have to calculate the loads on beam, which is W. So firstly, we have to calculate the loads on beam for span 1, which is 1 until 2, and then the design load is 34.54 kilonewton per meter, and then for the span 2 until 3, the design load is 37.60 kilonewton per meter, and then for the span 3, 40.96 kilonewton per meter. After that, we proceed with the calculation of action on beam, which we have to determine the moment of inertia by determine the B and also the H for beam and column, and then we have to calculate the stiffness, which is K is equal to I divided by L. So we have to determine the column stiffness, which is for upper and lower, and then for the each beam. And then we have to calculate the distribution factor, which is the formula is K divided by summation of K. And then we have to determine the DF for each joint, which is joint 1, 2, 3, and 4. And then the analysis of one level subframe will be proceed with the case 1. So for my part, I calculate the analysis, which is using case 1. All span design is permanent and variable load. All design permanent and variable loads is 1.35 GK plus 1.5 QK for the W calculation. And then we have to determine the fixed end moment from each column, from each joint or column. So the M12 is 21.77 kilonewton meter, M23 is 91.37 kilonewton meter, and for M34 is 98.88 kilonewton meter. So the moment distribution has been calculated using the Excel. So as the figure given, this is the total moment distribution that has been calculated for each joint and column. So the shear force, so we proceed with the shear force calculation, which is to determine the V21, which is we get 70 kilonewton, and then the V32 is 91.13, V23 111.91 kilonewton, and then for V12 24.99 kilonewton, V34 124.75 kilonewton, and lastly V43 94.98 kilonewton. So lastly, we have to construct the shear force and bending moment diagram for the vertical load only.
Assalamualaikum, my name is Nurusina binti Isa. My matrix number DF210070, and now we present the analysis of pad footing design. So this is the calculation for the pad footing located at 3A. So this is the specification. First step is to find the size of pad footing. First, we need to estimate the service action, and then assume that self-weight of footing is 10% of service load. So the area of footing required is calculated using this formula. The size that will be used is, for the width is 3.5, and the height is 3.5, and also the thickness is 0.5 meter. Then calculate the self-weight. Next, we will calculate the max soil pressure using this formula, and then equal with 47.59 kilonewton per meter square, which is smaller than soil bearing capacity, which is 150 kilonewton meter square, which is the size is okay. Then the next step is analysis. So we need to find the ultimate soil pressure using this formula, and then we got the P max and the P min. So from this result, we will calculate the bending moment at the column face. So this is the diagram for ultimate soil pressure for this pad footing. Next, estimate the main reinforcement. So first, we need to find the effective depth at axis X and Y. Then we will find the longitudinal bar. So using this step to find the AS required, the first step to find the AS required is to find the value of K. The value K will be used this formula, and then equal to 0.014, which is smaller than the K, but equal to 0.167, so the compression is not required, and then the value Z. Using this formula, and then equal to 0.990, which is larger than the 0.950, so we use 0.950. So next we will calculate the AS using this formula, and then equal to 1379 millimeters square, which is the AS required. And then for the bar we will use 21 H12, which is the AS provided is 2375 millimeter. And then we need to find the minimum and the maximum reinforced area. So we will find the AS max, we got 2298 millimeters square, and for the AS max using this formula, and then we will get 70,000 millimeters square. And next we will continue, we calculate the transverse bar. So to calculate the transverse bar, it seems like to calculate the longitudinal bar, and then for the AS required is equal to 1361 millimeters square, and then we will use 21 H12, and the AS provided is 2375 millimeters square. And for the minimum and the maximum reinforcement area is, for the minimum is 2240 millimeters square, and for the area maximum is 70,000 millimeters square. Next, we will estimate the shear. There are 3 steps in this part, which is the first is the vertical shear at 0.1 dig from column face. First, we need to find the average pressure at the critical section, and then calculate the vertical shear force, and then we will design the shear resistance using this formula. Then note that bar extend via critical section at 105 millimeter, which is larger than the 901 millimeters. So the ASL that will be used is 2375 millimeter, which is the AS provided. And continue calculate the P1 using this formula. The calculated value for K and P1, we will calculate the VRDC. For Vmin, we will calculate using this formula. So the value for VRDC is larger than VED, so it is approved. Then calculate the punching shear at parameter 2.0 D from column face. Firstly, we need to find the D, and then find the 2D, and then we will find the control parameter, which is U. Then the area within parameter will be calculated. Next, we will find the average punching shear force at control parameter, and then we will find the punching shear stress using this formula. Firstly, we need to find the beta using this formula. So from that value, we will use to calculate the punching shear stress. Then we will find the punching shear resistance, which is the VRDC equal to Vmin, using this formula, and then equal to 0.38 Newton per millimeter square, which is larger than the VED, that means it's approved. And then the last step in this part is to find the maximum punching shear at column parameter. And then find the column parameter, then the punching shear stress will be calculated using this formula, and then we need to find the beta, and then W1 using this formula. Then we can find the beta from the calculated value. We will find the punching shear stress, and then the maximum shear resistance is calculated equal to 4.5 Newton per millimeter square, which is larger than the punching shear stress, which is okay. Then we will continue to find the cracking. First, assume steel stress under quasi-permanent loading using this formula, and for the design crack width is 0.3 millimeter. And then the maximum allowable bar spacing is equal to 200 millimeter. First, the maximum bar spacing one, which is for the longitudinal bar, is equal to 172 millimeter, which is less than 200 millimeter, which is okay. And for the maximum bar spacing 2, which is for the transverse bar, is equal to 172 millimeter, which is smaller than 200 millimeter, which is approved. So this is the detailing for pad footing that located at 3A. And next, the calculation for pad footing located at the 3C. For this calculation, it seems like pad footing located at 3A. So here is the detailing for pad footing located at the 3C. Next, the conclusion for our project.
The project aimed to construct a reinforced concrete structure with an elevator, analysing the slab, frame, column and foundation. The analysis was conducted manually and with esteemed software, resulting in a 2D design of alternative analysis. The building design techniques were evaluated and designed in compliance with Eurocode specifications to determine how the techniques design affect the structural stability, strength and flexibility. The project applied reinforced concrete design concepts to the architecture of 4-story building, focusing on the critical roles of building elements like height, load, material form, number of bars, column and beam size, and also the construction requirements. Careful measurements, operation and strict adherence to Eurocode standards were essential in the project. In summary, the project yielded a thorough comprehension of slab, frame, column and foundation analysis in reinforced concrete constructions.